Alright gang, here we go. So this is Chem 1, Unit 2, Part 2. We're going to be talking about the history of atomic structure. This video is a little bit different. We're going to briefly go through things, and what I need you to do is hop onto the Google Classroom and look at the slideshows that I've put up there, especially this one, and for each of these things I've picked out a YouTube video that does a pretty good job explaining what's happening, and it's got animations and stuff, so it'll be a little easier to picture what's going on. I'm going to walk through very briefly what all of these guys did and kind of the basic setup of their experiments, but really those videos are the key to trying to figure out what's going on. Alright? So history of atomic structure. So there's this guy named Democritus, okay, Greek philosopher. He lived 400 years BC. Okay, and he developed the most early models of the atom. So what he decided is he's like, well, what if we just take something and keep cutting it up, cut it in half, cut it in half, cut it in half, cut it in half. And he theorized that eventually, or philosophized is probably more accurate, that eventually you get to a point where you get to an individual piece that could no longer be cut. And if you did manage to cut it, it would no longer be the same thing that it was before. Okay. Particularly, he said that these things were indestructible. He called them atomos. Okay, atomos. All right, and so that's where we got the name later for atoms. Okay, so because he was a Greek philosopher, the scientific theory hadn't really been developed yet. Okay, most of the time these Greek philosophers just kind of sat around and just kind of thought and argued with each other about what was going on. All right, so really he just philosophized it, but there was a distinct lack of any scientific evidence proving his thoughts, even though he was pretty close to correct. All right, so along came John Dalton, several thousand years later. And he started to use rough experimental evidence. Okay, he kind of built on the idea that Copernicus used. Remember Copernicus? He's the guy that said, he's most famous for saying that the Earth revolves around the sun and all that stuff. Okay, so about that time is when the scientific evidence, scientific theory really started to move. Okay, so he started using experimental evidence, and really he was all interested about the ratios in which elements combined. By the time he lived, we had a fundamental idea that there were specific elements, but he was very interested in how they combined and then studied the ratios. So he came up with what he's called, what we've dubbed the atomic theory. Okay. And it's got 4 postulates, and here they are. All right, that all elements are made of atoms and that they're indivisible. Okay, meaning you can't break them up. Atoms are the smallest particle of an element that still retain the properties of that element. Okay, so this is really key. If we take an element of nitrogen and split it in half, you no longer have nitrogen. It's no longer something that acts like nitrogen. It's going to act like the 2 new elements that you've broken it into. Okay, so that's his first postulate. The second, atoms of the same element are identical, but atoms of different elements are different. Last video we talked about how these elements are different from each other, right? They had a number of protons. John Dalton had no idea about subatomic particles. He didn't know about the proton, the neutron, or the electron. Okay, so he theorized that atoms, that if you had 2 elements or 2 atoms of nitrogen and you compared them to one another, they'd be absolutely identical in all respects. All right. But if you took an nitrogen and compared it to an oxygen, they'd be different. Okay, and then atoms of different. So that's the second one. And then the third one, atoms of different compounds combine in whole number ratios to form compounds. All right. So the idea that if you had water and it was made up of H2O, okay, that you couldn't ever have something that was like H1.20. This doesn't happen. That was his third postulate, that they always have to be whole number ratios. And then chemical reactions occur when atoms are separated, joined, or rearranged. Okay, but atoms of one element are never changed into atoms of another element. All right, that's the other key. So when you're having a chemical reaction, remember, so we say this word and we should automatically think about bonds. So when you have a chemical reaction going on, these bonds are getting broken or getting formed. And that's really the idea of John Dalton's idea. So he said that all elements are made of atoms, that they're indivisible. Okay, and they atoms of the same element are identical. Atoms of different elements combine in whole number ratios, and then chemical reactions are when these individual atoms are moved apart, joined, or rearranged in some way. All right. Next came up J.J. Thompson, okay, and he came up with he used what's called the cathode ray tube experiment. And in class, we're going to watch, or I'm going to show you a cathode ray tube, okay. Cathode ray tube, we'll see on the next slide as a picture, and essentially it's just a vacuum tube. All right, and he sent electrons through, and then he was able to pass. You could see these cathode rays, okay, and they're essentially, that's what they called them, but they were essentially just electrons, okay, and he was able to prove or show that when you shot these cathode rays through the tube and you introduced a magnet or an electric current, okay, that these electrons would start to bend one way or the other. Okay, and he noticed that no matter what gas he used, they'd always bend in the same direction. So and if he put the positive side on one side, the electrons would always be attracted towards the positive and repelled by the negative. Okay, so this really helped us discover the electron, and he developed what's called the plum pudding model. Okay, and the plum pudding model was essentially that there was like this general goop of positiveness, because we didn't know about protons yet. Okay, so there's a general goop of protonness. So like just a picture like a sphere of jelly. Okay, and this jelly was positively charged, so it's just a bunch of positive charges, just kind of like a goop, right? And then there were these things that were electrons that were just kind of like chilling, like are inside this goop. Okay, so they call it the plum pudding because it's just like pudding with plums stuck in it. Okay, so here's the here's a cathode ray tube. Okay, so he's got this tube. He's shooting electrons through, and then he can see that these electrons, these dots, represent the path that these electrons take. So they're able to get bent by the magnet. All right, so if you click this link right here, it takes you to a nice little video explaining exactly the cathode ray tube and stuff like that. All right, next came Ernest Rutherford, and he was credited with coming up with the gold foil experiment. Okay, let's see. So in the gold foil experiment, he had like this screen, a phosphorescent screen that was around it, around this little very thin piece of gold foil. So this guy here is gold foil, and then around here is this phosphorescent screen that would light up when positively charged or negatively charged particles would hit it. All right. So and then he would stuck an alpha particle generator. Rutherford also was big into nuclear chemistry and researching radioactivity and stuff. So he took a positive charge generator, or an alpha generator, and he'd be shooting in alpha charges. Okay, and they'd come in and it'd hit this gold foil, and he expected them to get, just go straight through. Now, what's interesting, in the vast majority of them would really just go straight through. These positive charges would just kind of come right through this gold foil, no big deal. But every once in a while, some of them would get deflected, and hit one side or the other, and occasionally even they'd come like right back and hit this screen. Okay, so this was like a huge discovery. Okay, that like he said it's kind of the equivalent of launching a cannonball at a piece of tissue paper and having the cannonball bounce back and hit you. Okay, it's like because these alpha particles are super strong, very heavy, very dense. Okay. And so this allowed us, to discover the nucleus. So he theorized that the plum pudding model is not quite right, that the atom is mostly empty space, but at the middle is a very small, very dense nucleus, and it happens to be positively charged where the neutrons and protons are. Okay, so he's credited with discovering the nucleus using his experiment here. Click this link here to help you, and it'll watch a video that kind of explains it with like little graphics and stuff. All right, and then finally, there's two more. There's Millikan, okay, with the oil drop experiment. Okay, Millikan oil drop experiment. What he did is he took a canister, okay, and he took a canister, and then he put two plates. So he put one plate up here and had like a little tiny hole right there, and then he had another plate right here, and he'd make one plate negatively charged, okay, and this plate positively charged, okay, and then he would spray in using, and now this is honest to God what it was called, and it is quite possibly my favorite name for anything ever. This was called the atomizer, okay. and he'd spray in little oil droplets using the atomizer. Yeah, you have to say it like that. Okay, so these oil drops would come in, and they, spray out, blah, 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 and then eventually they'd start, they'd fall through the hole, but they'd always fall in a straight line like this. Now, on one side, he'd put an alpha generator, very similar to Rutherford's alpha generator, okay? And then on the other side, he'd put he had like a little microscope that let you see what was going on. Okay, so these alpha generators would come through and hit these oil droplets and induce a charge on these droplets. And then these droplets, you'd expect them to fall because gravity pulls them down. Well, as these droplets got positively charged, they get dragged up towards this negatively charged plate. All right, and so they'd get dragged upwards occasionally, all right? And then using the microscope, he could measure how fast they'd get dragged up, and he'd notice that some of them would, continue falling down, some of them would go up, and then some of them would just suddenly remain stationary and just kind of float there. All right, so based on these measurements he made of these oil droplets, that they were going down or going up, he was able to determine the charge and mass of an electron. Okay, so Millikan, he found the charge and the mass of the electron, okay, which is actually pretty astounding because it's, a stupid small amount of charge, 10 to the negative 19th, and a stupid small mass, 10 to the negative 28th, okay? And so it's so small that it's equivalent to 0 AMU, all right? And here's another video. So if you click this link up here, you can see the video of the oil drop experiment at work, all right? Finally, James Chadwick, okay, he was much later, and he noticed, scientists, chemists noticed that there was something questionable about what was going on with their theory of the atom. That the protons, they could figure out pretty easily how many protons that an element had, but the mass of that element never matched, unless it was really, really small elements like helium and hydrogen. They never matched, that there was always way more mass to the atom than the number of protons. So they theorized that there must be some other particle, and James Chadwick is the one that really is credited with finding the neutron. Okay, so he used something very, very similar to the Rutherford's gold foil experiment. He used a polonium source which produced alpha particles, and he shot them through beryllium. Okay, now beryllium would absorb these alpha particles and shoot off neutrons. Now they didn't know what these neutrons were at the time. Okay, he just kind of experimenting, and it hit this paraffin wax, which would stop the neutrons, absorb them, but then protons would get shot off, and then he'd use a Geiger counter, which is a special device to count the number of protons that are hitting something. And we'll talk about, once we get to nuclear chemistry, how a Geiger counter works. All right, so watch this video that's right here in the Google Drive, and or download the PowerPoint and watch this guy here. It does a really good job explaining exactly what's going on. All right, so that's the end of part 2. Do your practice problems and let me know if you have any questions. All right, I expect you to know kind of the general idea of what happened with each of these guys, their experiment, generally how they worked, what they proved.